Our next speaker will be Dr. Arti Singh, who's from the agronomy department at Iowa State.
Yes, no, I'm good. Thank you so much, Eddie, for the introduction. And thank you so much, organizers, for inviting me. And today, I will talk on rapid advancements in phenotyping through data-driven deep learning. So since I'm on a time crunch, I'll just go to my talk right away. So in today's talk, I'll be talking about challenges in successful AI application, and then I'll talk about motivation to work on insect problem, and then I'll talk about challenges in working with insect data, and then insect classification web app which we have developed, and last but not the least, some ongoing current work. So in 2014, when I started working in plant stress phenotyping problems, I realized that at that time we had data collection as a bottleneck. But soon as we started using UAVs and robots, then we have another bottleneck. Data collection was no more a bottleneck. Then we have a data annotation as a bottleneck. And data annotation can be a major bottleneck when we are trying to use these deep learning models, because we need a lot of data to train these models. So how to get over this data annotation problem? So we have these data challenges. In case of data annotation, as I said, collection of large label data can be a problem. So here you can see this is a poster, this is an image from a poster which my PhD student Ashlyn was presenting, where we were trying to do SDS severity, and we have to put these bounding boxes in each and every leaf to do individual leaf level severity. To do that, we have to put for these leaf images manually these bounding boxes, and then the model gets trained to put these bounding boxes on maybe 1,000 or 10,000 images. So this is a huge challenge. And we have these annotation tasks can be like marking disease regions or assigning these ratings when it comes to stress severity. So amount of in-domain data, or we call in-domain label data, is another challenge. So in case of plant stress phenotyping, we are thinking whether we should use in-domain data when we are training these deep learning models, or we should use out-of-domain data. Out-of-domain data is like these, we have these models, pre-trained models, where we have trained it on ImageNet or CocoNet, so can we use that? Another challenge is size of pre-trained data set. So when we are training these deep learning models, what is the size of pre-training data? Does that play a role? And then there is a class imbalance data. So when we are training these various models, we have a lot of classes. So what happens with classes? Do we need balanced data or we need imbalanced data? The second kind of challenge is modeling challenges. We have a deep learning model, so how to initialize this model? And then we have model selection challenge. Which backbone architecture we should use? We have like ResNet 18, ResNet 50, ResNet 110, or any other backbone architecture. And last but not the least, the challenge is supervised versus unsupervised transfer learning. So in my research since 2014, what we are trying to do is we are trying to close the gap between supervised and unsupervised learning by how can we reduce this amount of label data? How can we reduce this annotation? So when we started in 2014, our data set was small, the problems were simpler, so we were using traditional ML models. As we move on to more diverse and more complex data, we started using the supervised DL model, where we are using transfer learning. And from last few years, we have been using these self-supervised learning to counteract this data annotation challenge. And I'll come now why self-supervised learning. So you see here, in case of supervised learning, we need this huge manual annotation. We need, for example, we have images of a cat. We have to label it as a cat. for image of dog, we have to label it as a dog. But in case of self-supervised learning, what we are trying to do is we are removing this manual annotation bottleneck, and we are changing it to automated labeling. So now, and this is in case of self-supervised learning is called pretext task. We are exploiting the data property. So we are using these images, and we are just rotating it. Or we can have these colored images, and we can ask the model to predict whether they are grayscale or not. So basically, the idea is that here we are generating a lot of labels. And the supervised learning model learns when it is training for this pretest task, and once it learns the representation, these rotations, and it's also learning the underlying property of this data set, then we can transfer these learned representation to the downstream task, which is classifying these images into a dog or cat, but with lesser data, not lot data. So till 2019, or I should say till 2020, I was working on disease problems, and I was not thinking about any other problem. But something happened in 2020. So I'm a mung bean breeder. It's a new crop. And for last 4 years, we didn't see any problem with our mung bean breeding. But in 2020, what happened was we saw complex insect pest attacking mung bean. So earlier I thought it's a heat stress because there was flower drop. And by the time I could see, because I was going in field in afternoon and I could not see these insect pests hiding under the canopy. And by the time I could sense it that, hey, this is an insect problem, it was a little late. In 2021, I'm looking happy because you can see I knew that, hey, now we can put these sticky traps and we can take control of these insects, and we started collecting data for insects too. Another thing was happening in 2021 when we organized this machine learning for cyber agriculture workshop. One of the farmer, Dave Wilton, he was seeing these fall armyworm, and we all saw this because fall armyworm started marching from southern states like Texas, Florida to Midwestern states. And this is what Dave said in one of the meetings in 2021, that, hey, Artie, we are seeing these fall armyworm, and they decimated my plots. How can we detect, how can we control? So we were, I was having a meeting with Matt Carroll, one of the students in our zoonomics group, and I said, hey, Matt, can we somehow get the data from the satellite and see what happened before the fall armyworm attack? And we could sense that with that data, with satellite data, we can locate that, yeah, there is an attack going on, and if that detection work was done earlier, we could have prevented, the farmer could have sprayed and was able to save his alfalfa plots. So with that, from 2020, we started collecting this insect data set. And in 2021, we collected around 30,000 images of insect pests in 30 different classes. In addition, we came across this INET data from a challenge from 2021, where they had 660,000 images. And it's a huge data set. And with ISU data and INET, we started framing these problems. So here you see a PhD student, which is co-supervised by Dr. Ganapathy Subramaniam, who's sitting in the audience. And we started working on this problem. So there are a lot of challenges when you work with insect pest data set. So you can see here in first, the challenge could be that there is variation within the species. Here you are seeing the bean leaf beetle image, and you can see these bean leaf beetle can have different patterns from having these spots to without spots. The second challenge is these different insects can have similar color or pattern. Here you can see southern corn rootworm, which has these spots, but bean leaf beetle also looks similar with these spots. In case of western corn rootworm, we have these stripes, and cucumber beetle has exactly same color and pattern. It's very difficult. It's a fine-grained problem. It's not moving. Yes. So the third challenge is we have diverse background and a small foreground. So these insects are very small when we take pictures in field. And the fourth challenge is that these insects pests can have multiple stages. Like fall armyworm can have a moth, and it can have a caterpillar stage. The fifth challenge is that we have a large number of class imbalance, as I said previously when I started my talk. And when we have these large class imbalance, we see this this tail distribution, you know. So we see long tail distribution where we have these classes where we have rare classes where we have less data set. So this is also one of the challenge when we are dealing with insect pest data set. And last but not the least, the challenge could be that we have these multiple insect pests in the same frame, so overlapping objects. So we started using this self-supervised pre-training method to see how it can help us to address those challenges like how much data, in-domain data versus out-of-domain data, how to pre-train. So first question we addressed was data size. And we use this 66,000 versus 660,000 INET images. So this is in-domain data, insect data set, and we are using ResNet 50 architecture, and this is a self-supervised method. And we found that when we are increasing the data size, our model accuracy is good. So this gives us that we need more data. But then we also tested single stage versus multiple stage transfer learning. So here, you already saw this. This is a single-stage transfer learning when we are pre-training this self-supervised method on unlabeled data, and this could be out of domain or it could be in domain. In this case, we are using in-domain insect data. And then we are fine-tuning on very less data from our insect model, and this is supervised classifier here we are using. The second stage is we have these multiple stages where we are pre-training on large out-of-domain data, and then we are using self-supervised, and lastly, we are using very less data for fine-tuning using supervised classifier. So basically, in this case, we were testing like 15 different settings of one stage versus multiple stage. And for this problem, after testing around 15 different levels of transfer learning, we came to a conclusion, a winner model that gives us insect pest classification accuracy the highest. So here, the winner model is when we are using pre-training data from out of domain. And in this case, we used a RegNet model, and this is a backbone architecture, and we used Instagram weights, which was trained on billion images. Can you imagine? This is billion images is huge. And then we are fine-tuning using in-domain data, and this in-domain data is our INET plus images which collected. And again, this is not a small data when it comes to insect pest. It is 2 million images. And when we are using this one-step transfer learning, it is giving us 96.3% per class accuracy, which is huge, again. And our top one accuracy is 97.8, and this is for 142 insect pest classes. 142 insect classes is huge. And here you can see that when the 99% is, we are finding that monarch butterfly is the one which is classified with 95% accuracy, and clover looper is getting classified with a prediction accuracy of 66%, which is pretty low, but it could be because it is green in color and the background is green. So with this winner model, we created an app. And the beauty of this app is, as I talked to many of you, I showed you yesterday that how this app works, that this app not only classifies the adult stage, but it also classifies the nymph stage. In this case, spotted lanternfly is an invasive pest, and it has been spotted in Iowa, in Dallas County, and it can identify both. In case of Lygus species, which is one of the pests, which I was not able to recognize in 2020 because it looked like aphid. So it can identify both. And again, like a ladybird beetle, it can vary from one spot, 2 spot, 18 spot. It can also identify these various kind of ladybird. And the beauty is that I didn't know till I started working on this problem that not all ladybirds are our friend. And our app can differentiate between predator and pest now. So this is amazing. So why I feel that this is a huge success? Because I have worked on diseases, and I always wanted to have a model which can give a very high accuracy. So we can create into an app so that our farmers or stakeholders can use with high accuracy. And one thing I forgot to tell, that we also added this, to increase the trust, what we call uncertainty quantification or out of distribution thing, so that when we are testing it on something like a glass or a water, then it says, hey, I'm not uncertain, and that way it is increasing the trust of the app. And now I'll quickly shift to the current work. So right now we are trying to expand this work from 142 insect to 2,500 insect species, and then the next level is, can we extend this to 10,000 species classification? But since we are also working on, we are also moving into detection problem, where we are trying to use these robots to detect. But in order to use these robots to detect, we have to put these bounding boxes around these insects, because classification algorithm is not going to work. So what we are trying to do is we are moving to zero-shot detection of these insects using these natural language processing models. Till now, we were using these image processing model, but now we are also combining natural language processing models. And so here you can see that this is very coolest part. This work is done in collaboration with Chinmay Hegde, who is in NYU, and Dr. Bhaskar Ganapati Subramaniam. And here you can see, like, without any training, just giving a caption for these insects, we can put up bounding boxes. So now, can you imagine, we have 13 million insect data set. By using this zero-shot insect pest detection model, which is called as CLIP model, it's called contrastive language imagery training. Now we can put these bounding boxes, and this is known as prompt engineering. So what we are doing here is we are giving a caption to the model that, hey, look for a beetle which has a red hat, and then it is able to identify all the beetles in 13 million data set, and it is able to put these bounding boxes. And we found that this model has 93% accuracy, which is huge. And so this all work is feeding into our CoLS app, which is led by Dr. Shamik Sarkar and our Soinomics team, along with our Illinois collaborators, Girish Chaudhary and Girish Krishnan. Here, the idea is to close this sensing, modeling, and actuation loop. And here you can see we are using these dexterous robots, which are going to survey the canopy, and they have this camera on their dexterous arm. And once they're surveying this canopy, they're identifying and looking for insects. And in this case, it is as soon as it sees the insect, the data goes into the model, and it says that, hey, does this density is enough? The population of an insect is enough. If it has reached this economic threshold or action threshold, then it tells this dexterous arm to spray or spot spray. So this is where we are going to close this sensing, modeling, and actuation loop. And this is where our detection work is going to feed. And we are very excited that in collaboration with the University of Illinois, we have been able to see that our classification app is still working to identify this Japanese beetle. Here you can see that this dexterous robotic arm is trying to look for this Japanese beetle, and as soon as it sees, it is predicting that, hey, this is Populia japonica, which is Japanese beetle. So with this, I would like to end my talk, and I would like to acknowledge funding agencies, excellent group members, my students, postdocs, and my technician. And then in the end, I would like to thank our Soinomics team. And this Soinomics team is just not about these PIs, but we have very hardworking students, our postdocs, and our technicians. So thank you so much.